Hey everyone, so we're looking at section 4 today. This is just an extension of what we did in section 4.3. We're getting just a little bit more detailed in our equation solving with logarithmic equations and exponential equations. So we're actually just going to be doing the first four examples of this handout, and I'll talk a little bit about the applications over here, but we're not going to be really working on the applications. So like I said, just these first four examples. So let's start with our first one over here, and we're looking at the equation log of 2x plus 1 equals 3. Now, of course, they're asking us to solve these equations, which means we actually have to find our x value. Okay, so you're trying to find your x variable here. So the first thing you should see that our 2x plus 1 is inside the logarithm, right? So that means we need to find a way to get the x outside of that logarithmic expression. So what we're actually going to do here is convert this into an exponential form. So remember our rule for converting it from logarithms to exponential form. So let's say if you have log of x with base a equals y, when you are converting this into an exponential form, we take that base a, raise it to the exponent of y, and this will equal our answer x. So you can see this is a log over here, right, which is a common log, and that means our base is going to be base 10. So when I convert this into the exponential form, I will take this base 10, raise it to my exponent of 3, and this will equal the value 2x plus 1. So just using this rule over here, we will convert this from logarithmic to the exponential form, and now you can see it's going to be pretty easy for us to get that x by itself. So let's go ahead and write that 10 to the third. Go ahead and multiply that, so that will actually come out to be 1000, and then we want to get the x by itself, so we'll start by subtracting that 1, so it cancels out, and of course 1000 minus 1 will give us 999. We've got 2x on the other side. To get x by itself, again we'll divide both sides by 2, so these guys cancel out, and you get x equals, as a fraction, 999 divided by 2, or if they want a decimal answer, you can write this as 499.5. Okay, so either as a fraction or as a decimal. Now the one thing we do want to do after we finish getting our answer is actually check our answer and make sure our calculations are correct. So we're going to take log of 2 times x, which again x is 999 divided by 2, plus 1, and you know what, let's go ahead and use brackets over here, and this is equal 3, and of course we're just trying to verify that we'll get a true statement. So since I'm multiplying 2 with 999 divided by 2, this 2 and this 2 can cancel each other out, leaving us with log of 999 plus 1. And of course log of 999 plus 1 will become log of 1000. And if you just plug that in your calculator, you should see that we will end up getting 3 equals 3. So since we get a true statement, we know our answer is correct for problem number 1. Okay, now same thing they're asking us to do here is solve example number 2. So let's go ahead and take a look at this guy over here. So example number 2, we are given log of x minus 1 plus log of 3 equals log of x minus log of 4. So the first thing you should notice is all of these are the same logarithms, right? Because this is base 10, base 10, so these are all common logs. So we can actually use our rules of logarithms to combine these into single logs. So we'll start with the left hand side first. Go ahead and combine these two into a single log, and we'll do the same thing on the right hand side. go ahead and combine these into a single log. So since you have a plus sign on the left-hand side, that means you have to use the product rule. So that's going to be log of, and remember product rule, when you have a plus sign, that means you multiply your logarithmic value. So you are going to take x minus 1 and you're going to multiply it with 3. On the right hand side, you have a minus sign. So the minus sign tells us we use the quotient rule. So that will be log, and then quotient rule, of course, x goes on the top divided by 4 goes on the bottom. So we go ahead and convert these into single logarithms. Now on the left hand side, we'll need to take this number 3 and distribute it inside the parentheses. So that will end up giving us 3 times x is 3x. 3 times 1 is 3, so that will become minus 3. And of course we have log of x over 4 on our right hand side. Okay, so here you will notice that we have the same log base 10 and log base 10 on both sides, right? So now you are actually bringing in your 1-to-1 property. So remember, 1-to-1 property, and again let me write that down, says that if you have the same base logarithm on both sides of your equation, then we can say x1 is equal to x2. So this is the 1-to-1 property of logarithm. So we can use that here. And that means you can basically just say 3x minus 3 is equal to log over 4. And that's what the 1-to-1 property helps us do. Now, as you can see, we have x term on the left-hand side and x term on the right-hand side. So we want to try and get our x terms on the same side. So the first thing I will actually do here is go ahead and multiply both sides of our equation by 4. Get rid of that denominator here. Distribute that 4 inside the parentheses. So that will of course end up giving us 12x minus 12 equals x. We want to get our x on the same side, so I'll go ahead and subtract this 12x. Move it to the right hand side. Okay, so it cancels out from the left, and let's see, we are left with minus 12 on the left hand side. 1x minus 12x will of course end up giving us negative 11x. And the final thing would be to get x by itself, divide both sides by negative 11. So these guys cancel out and you end up getting x equals 12 over 11, right? The two negatives will become positive and you end up getting positive 12 over 11 as your value of x. Okay, so just like we did with the previous example, once we get our answer, we do actually want to check our answer and make sure it's going to work. So let's take a look at doing a quick check for this guy. Okay, so that would be log of 12 over 11 minus 1 plus log of 3 equals log of 12 over 11 minus log of 4. Okay, so again you can use your calculator here, but let's go ahead and simplify this. So if we're doing 12 over 11 minus 1, that will basically end up becoming 12 minus 11 over 1, or basically 12 log of 1 over 11 plus log of 3, and then these guys of course, oops, that should be 12 over 11 minus log of 4. Now you can do decimal approximations on both sides and just make sure that you are coming up with the same value. So let's see what these decimal approximations come out to be. So when we do our decimal approximations, you can see we have approximately the same value on both sides of our equation. So again, we can say this is a true statement and you are good to go. Now, if you don't want to do decimal approximations, then you will basically have to repeat your product rule on the left hand side, quotient rule on the right hand side, and see that way if you are getting the same logarithmic value on both sides or not. Okay, so this was our example for problem number 2. Alrighty, now we are getting into the exponential form of the equation, and we want to see what kind of answers we get from here. So let's look at our first example for the exponential functions, and this one is 1.05 raised to the power of 3t equals 8. So as you can see, our unknown value, the t variable, is in the exponent, and to be able to find that t, we need to bring it down from the exponent to the base level. So that means we have to use the base change formula. So your base change formula is going to be basically, if you have the original function as log of m with base a, you can write this. Now remember, this will be base b, which can be base 10 or base e, so you can use a common log or a natural log here, and you would put log of m with base b on the numerator and log of a with base b on the denominator. So basically this m goes on the top, this a goes on the bottom. Okay, so that's one way to do it. Now remember, the other way could be is like you have this expression over here, you can take a natural log on both sides, or you can take a common log. I'm just going with the natural log here. So when I take the natural log like I did, I can now use my power rule to bring this exponent down to our base level, right? So we can now have 3t multiplied by natural log of 1.05 equals natural log of 8, to get 3 and natural log of 1.5 on the other side, and get t by itself. Of course, we need to divide by 3 and the natural log of 1.05, so divide by 3 times natural log of 1.05. Okay, so this will cancel out the t from here and the natural log of 1.05, leaving us behind with just the variable t. And now you can put this in your calculator and go ahead and solve this. So in your calculator, what you can do is first type in natural log of 8, make sure you close that parentheses, divided by 3, hit enter. Okay, then whatever answer you get, on that answer you will once more divide it by natural log of 1.05 and hit enter again. So basically we're dividing by 3 once, you get your answer, and then you're dividing that answer again by natural log of 1.05. So we're just breaking it up into 2 steps. And when you go through this example, you should end up getting an approximate value. And again, since we're using the base change formula here, we're going to round this to 4 decimal places. So approximately this comes out to be 14.2067 when we round it to 4 decimal places. Okay, so you can see, to simplify this, we use the base change formula and then get your t by itself. Okay, and then the last problem we wanted to look at was this number 4 over here. So that's 3 raised to the power of x minus 1 equals 2 to the x. So again, you will notice that both our exponents have the unknown variable x in them, right? So again, we have to use the same version of base change formula here, but it's going to look a little bit different. So just like we did before, on both sides of our equation, we'll use log this time. So let's do 3 raised to the power of x minus 1 with a log on the outside. And same thing, apply a log here on the right hand side. So again, you could have used natural log here, you can use common log here, it doesn't matter which one you go with. So I'm going to take this value of x minus 1 and bring it down to our base level by using the power rule. Same thing on the right side, I'll take this exponent x and bring it down in front of its logarithm. So since I have x minus 1 as my exponent, I'm going to put it in parentheses and then multiply it with log of 3. On the right hand side, you will end up getting x times log of 2. Okay? Now what we're going to have to do on the left hand side is we have to take this, because this is one number, this is one value. You have to take that log of 3 and distribute it inside our parentheses over here. So that will give us, let's see, x times log of 3 minus 1 times log of 3 would of course be log of 3, and then we have x times log of 2 on the other side, right? Okay, so obviously now we want to get our x terms on the same side. So what I'm actually going to do first is go ahead and move that log of 3 to the other side. Okay, and then what I'm also going to do is subtract this x times log of 2 and bring it over here on our left hand side. Okay, so that will end up giving us x times log of 3 minus x times log of 2 on the left, and on the right hand side we will have just the log of 3 left behind. And of course you can see that log of 3 does not have an x value for it, so we wanted to try and get it aside by itself. Now in my left hand side you will notice both my terms have an x term in common, so I'm going to take that x term outside as my greatest common factor, and you will be left behind with log of 3 minus log of 2 here, and I'm going to put that in brackets. Keep the same term on the right hand side. And of course our goal was to get x by itself, so now that we have factored out that common x from both our terms, you just want to go ahead and divide both sides by this log of 3 minus log of 2, and we will have isolated our x term. So cancel these guys out. We are left with x equals log of 3 divided by log of 3 minus log of 2. Now when you type this in your calculator, you will of course do log of 3, and then when you do divided by, open parentheses, then do your log of 3, close parentheses, minus log of 2, close parentheses, and then close the parentheses one more time for this guy, so that your calculator knows we are dividing by this entire subtraction of log of 3 minus log of 2, and then you will hit your enter. Okay, and again guys, we will be rounding this to 4 decimal places, so our x value will come out to be approximately 2.7095. So basically, like I was telling you, this is still using the concept of phase change formula, but it's going to look a little bit different, because in this case we had our unknown value of x on both sides of our equation on both exponents. So it's going to of course take us where we had to combine those x terms, bring it on the same side, and then isolate that x. Okay, so this is what our example 4 solution will end up looking like. Now, like I said, I just kind of wanted to discuss these applications with you guys a little bit. So the first one here is talking about the radioactive dating model. So they're talking about half-life in this case, and of course by the term half-life we mean that over time half of that material, because it's a radioactive substance, will start decaying, which means it will start losing its mass. So over half its life, if you started out with, let's say, 1 gram of this radioactive substance, then after its half-life is passed, instead of 1 gram, you will now have only half a gram of that left behind. Okay? So, and like in this example, they're saying if the half-life of a substance is 1 million years, so basically we're saying again, like I said, if you start out with 1 gram of the radioactive substance, after a million years, only half of a gram would be left. So that's how, we normally do these radioactive dating, or sometimes we call it carbon dating if you're looking at the carbon 14 molecule, right? And so based on that, you can see we are using this formula to basically just see if 40% of the original amount is left. That means you have actually gone beyond half-life, right? Because at half-life, you should have had 50% of the substance left behind. So if only 40% is left, that means we've gone a little bit longer than 1 million years. So you can kind of look through this example. So this is where your solution starts for this, and you can kind of walk through the steps and see how we came up with the answer. And you can see this is a pretty involved process, and right here, as I was telling you, it's going to be more than 1 million years because you have lost 60% of the substance, right? That has decayed, which means it has been more than 1 million years. Now, this same formula, and this formula is the same type as your continuous compounding formula, the one that I call as the Pert formula, right? It's in the same form, and you actually have another application, which is this one here, Newton's model for cooling. And you can also use the same idea here, where they are saying a cup of boiling water is placed outside where the temperature is 12 degrees Fahrenheit. So of course, if you're taking a cup of boiling water, which is going to be at 212 degrees Fahrenheit, and you're going to put it outside where the temperature is only 12 degrees Fahrenheit, the temperature is going to start falling. So they're saying in 4 minutes, the temperature is only 102 degrees Fahrenheit, and they want to know how much longer will it take for the water to reach 82 degrees Fahrenheit. So again, you can kind of see that they go through these calculations here. Again, of course, we're using a form of the base change formula, and as you go through the process, they're basically saying after you have spent approximately 5.3 minutes outside with this cup of boiling water, it will have fallen down to 82 degrees Fahrenheit. So this example here, the Newton's cooling method, is actually also something that law enforcement also uses, when they are trying to estimate the time of death. If they found a body and they want to know how long it has been since this person had deceased, they will use this Newton's model for cooling to kind of help them estimate the time of death. So just some different applications that I wanted you to be aware of. But like I said, we are not going to be doing these examples. So you just need to concentrate on examples like these first 4 examples over here. Okay, guys? So if you have any questions, again, let me know. I will see you guys in class. Stay safe, be careful, and have a wonderful day. See you later. Bye-bye.